Hi, I'm Paula Figueiredo and I'm a researcher at North Carolina State University. And today I'll talk about active tectonics in the southwest of Portugal, quaternary deformation analysis in the low tectonic rate area. Portugal is located in Western Europe, close to a plate boundary, which is the plate boundary between Eurasia and Africa that converges at the rate of about 4 to 5 millimeters per year. The plate boundary is very well defined east of the Azores island, but when it approaches the Gulf of Cadiz, the deformation gets more distributed and the plate boundary is not as evident as a single structure. This is the map of the Gulf of Cadiz, and there are many structures. Most of them, they are reverse faults, they are thrusts, and there is also a very large strike slip system. There is one smaller normal fault, which is the Pereira de Souza fault. And inland, there are also many other structures that have quaternary deformation and generally have smaller sizes than the ones on the offshore. Regardless, all of them, they are capable of generating moderate to large seismicity. This is an image of the structures in the offshore and a map also of the neotectonic structures as they are mapped with the Portuguese neotectonic map and overlapping DEM after 30 meters. You can see that there are a lot of features in the landscape that they are not mapped as active structures. And the reason for this is that we have a lot of structures that they have been reactivated through time. They're through the two main orogenies that were expressed in Portugal, the Hercynian and the Alpine orogenies. And there are some structures that they have a really good expression in the landscape. However, they are not active. In fact, most of the landscape is eroded and it's poorly preserved. There is a Miocene peneplain that has been now strongly incised by the drainage and it's mostly gone. And some landforms, they have been reoccupied since the Miocene several times through time during the Pliocene and the Quaternary. Another thing is that all of these structures, they have really low slip rates. And if you think that the plate boundary has 4 to 5 millimeters per year of convergence, which is about 10 times less than the plate boundary in California, it's easy to understand that each one of these structures is taking a little bit of that deformation, and they will have slip rates in the order of 0. something to 0.0 something millimeters per year. So the tectonic rates are really low and they are difficult to characterize. Another big feature inland is that there is a prevalence of the erosional processes in comparison with the positional ones. So we don't have a lot of quaternary sediments and there is a lot of incision. This incision is also correlated with uplift. So there is it's easy to assume that there is an increase in uplift towards the south of Portugal. And if you think about this and you try to look for evidences of uplift along the coastline, these are two examples of different coastlines located very close to each other. This A site here is located on the western coastline facing the Atlantic, more exposed to the big storms. And it's easy to see the very high cliffs. They are a big feature here. And the cliffs can be as high as 120 meters. And the creeks are really well incised on this regional abrasion surface here. There is also a lot of cliff retreat associated to the Holocene high stand. This regional abrasion surface is believed to be one of those landforms that generated during the Miocene and then was later reoccupied during the Pliocene and the Quaternary times. And it's also visible on this other site here on the background, and you can see that it evolves to this relic landscape, which is this igneous massif of Cretaceous age. But by the coastline itself, the cliffs are really small, as high as 20 meters at the most. And between the coastline and the background regional abrasion surface, there is a landscape that gradually decreases elevation towards the ocean to the south and is associated to the Quaternary sea level oscillations that shaped this previous existent landscape. This is again the regional abrasion surface that we know that was reoccupied the last time during the Quaternary and is actually deformed and displaced by an active fault system of a left lateral strike slip with a minor component of reverse. And we try to differentiate how much of this deformation was pre-Quaternary and Quaternary. So we did a lot of geological and geomorphic mapping, trying to constrain the more active strands of this fault system. We also apply morpho-tectonic indexes, trying to highlight where these more active strands were. And once we have identified them, we will actually run geophysics across them to highlight the fault zones and to recognize how wide they were. And in this case, we were able to recognize a fault zone between the Miocene and the Paleozoic in areas where you would have suitable deposits. We will trench them and investigate the formation associated with them. So in particular for this fault system, we were able to corroborate that it had the formation at least since the middle Pleistocene, because there is a level of soil that is displaced about 1.5 meters. Remember that this is a strike slip system, so this is a partial deformation associated to that. We were not able to constrain how much lateral deformation has been accumulated since the middle Pleistocene. And in another place along this fault system, we were able to observe that the deformation was sealed by sediments slightly older than the Holocene. So we do know that this fault has not ruptured during the Holocene. To investigate the coastal uplift, we focus on older references and more younger references. This is the abrasion platform again. And on this abrasion platform, there are some marine terraces that are poorly preserved. And we were able to recognize a complete sequence of a marine terrace. And we dated the basal gravel layer with cosmogenics, and we obtained an age of about 2 million years for it, which allow us to estimate an uplift rate of 0.04 millimeters per year, which has been recognized in other places in Portugal, and it's kind of the background uplift signal for the South country. But when we look to the more recent deposits, the last time that the sea level was higher during the last interglacial or marine isotope stage 5, we were able to estimate an uplift rate of about 0.11 millimeters per year. So it's an increase of about 3 times more than the background signal of uplift. And we do know that there was a change in time that we are not able to tell exactly when it happened, or even spatially where what is constraining this uplift, because the marine terraces are not present everywhere in the area. So to investigate these questions, we actually decided to step out of the initial study area, which was this southwest area here, and extend an analysis to all the south of the country, so that we can compare analysis on where we were working to the neighboring areas. And we decided to do this by applying morphotectonic indexes to the basins that were outflowing to the Atlantic. We made a selection of the indexes based on the literature and what we will think that they will be the more suitable, considering that they will cross different types of structures and with different types of kinematics. It was thought that many of them might not be suitable, because the slip rates were so low, and in the literature there are indications that it has to be a larger amount of deformation so that you can actually apply the indexes and detect the deformation. One index that we were very hopeful to be a very good approach was the channel steepness, the KSN, which unfortunately did not work for our area. The reason for that, we believe that it's associated to the DEM that we were using, the available one for us that had a lot of noise, and to the fact that the landscape had a really small amplitude in elevation, and the gradient of the channels was very slow, very low. However, for instance, even in a very large area that had a really low gradient and a small elevation in amplitude, we were able to apply the stream length anomaly maps, and we were able to recognize anomalies associated with structures that were previously mapped. These structures are not very well understood, but yet we were able to corroborate that they are active and that they are actually creating an anomaly in the system. Another interesting analysis was that the basin is becoming symmetric with time, and we infer that this is associated to a change in vertical signal, in this case, a decrease in uplift and an increase in the subsidence in a specific area. So most of the indexes provide us as numerical numbers, and we were trying to investigate a way to correlate all of this and to have actually a meaning that we could understand with our morphology and geology. So we decided to plot the numbers along the coastline and see if there were any difference between the different areas. So in this graph here, there are 5 indexes, and there are references of the morphology and the 2 main faults that cross the coastline, the Alentejo-Plasencia fault and the Quarteira fault. And there is not a big difference caused either by the faults or by the morphology, but there is an index that provides a significant change, which is the valley floor index that was developed by William Bull to be applied to the mountain front ranges and association with alluvial fans. And there is a really large decrease in the number, meaning that the valleys here are all more narrow and more incised, except to these 2 basins that they correspond to a very broad valley, and this corresponds to the 2 very large rivers that they flow towards the south coast. But this is also consistent with an area where we were able to recognize a higher uplift rate, which is more or less this area. And there is not a single structure that can explain this uplift, so we were not very well sure of what was causing this uplift and how. In parallel with this study, we were also investigating the area with geodesy. And our goal was initially to detect small changes between faults, but we end up realizing that all of this area was behaving differently from the rest of the country. The blue ones are the temporary GPS campaigns, and the black ones are the permanent stations. And it's really obvious to detect that all of this area is behaving differently than the rest of the south of the country. And this is consistent as well with the changes inferred by the morphotectonic indexes. So we are proposing the existence of a new active structure that is still not very well expressed at the surface, but that is causing already influence in the landscape. And it's recognized also by the geodesy. So to conclude, low tectonic settings can be really hard to study, and they might not express any sort of seismicity for a long time, but they are capable of generating significant seismicity. And when you are working in an area that is a low rate tectonics, competing with all of the other surface processes, it's probably wise to do a cross correlation of indexes and see which one might be telling you some information about the evolution of the landscape. And finally, we should also plan to support our data with other techniques and other methods, and using also other disciplines as geophysics, geodesy, and all of this, because they will provide us some more information that might be very useful for us to interpret our own observations. And that's it. Thank you. Obrigada. And please feel free to reach out if you have questions. Thank you.